By now we're all familiar with the basic rules of exponents and how to calculate them. But those exponents have always been positive whole numbers. We're going to start to complete our ideas about exponents by moving into zero and negative exponents. We're going to explore what happens when exponents are not positive integers, but are also zero and negative integers. And that's going to be the focus of this Show Me. Let's start by filling in these two columns of calculations so that we can get a sense of how patterns drive the conclusion that mathematicians reach about zero and negative exponents and what they must mean. 3 to the third power is 3 times 3 times 3. Well, 3 times 3 is 9, and 9 times 3 is 27. 3 squared is 3 times 3, which is 9. 3 to the first power is a single 3, which is 3. 3 to the 0 power is something we haven't thought much about before now. Look at the three numbers that precede it. To get from 27 to 9, we multiplied by 1 less 3. Effectively, we divided 27 by 3 to achieve the result of 9. In the same way, 3 to the first has 1 less 3 involved in it as a factor, as did 3 squared. 9 divided by 3 is 3. It looks like we're dividing by 3 each time. Let's continue that pattern to find the other numbers. 3 divided by 3 is 1. 1 divided by 3 is 1/3. So it looks like 3 to the negative 1 would be 1/3. And then 3 to the negative 2 is 1/3 divided by 3. Well, 1/3 divided by 3 is the same thing as 1/3 times 1/3, which is 1/9. So that's how we would complete this table. And it appears that when we have a zero exponent, the result is going to be 1. And when we have a negative exponent, the result is going to be the same power, but it's going to be placed in the denominator of a fraction. Whereas before, when the powers were positive, the power was placed in the numerator of a fraction. Notice that the negative exponents don't make the results of the calculations negative. All they do is define where the power should be. If the exponent's negative, the power should be in the denominator. If the exponent's positive, the power should be, as it always has been, in the numerator. I don't know that we ever thought of 27 as a fraction, but it is a rational number and can be written as 27 over 1, in which case our power did indeed end up in the numerator. Let's do the same thing for negative 2. Notice that negative 2 is in parentheses. You must put parentheses around a negative number if you intend to multiply everything about the number into the power. If you were to leave the negative sign outside the parentheses, you would be writing in a completely different expression, and we will be talking about that later in this Show Me. For this example, negative 2 to the third power is negative 2 times negative 2 times negative 2. Well, negative 2 times negative 2 is positive 4, and 4 times negative 2 is negative 8. Negative 2 squared is negative 2 times negative 2, which is positive 4. Negative 2 to the first power is simply 1 negative 2, written by itself. To get the result for negative 2 to the 0 power, we do as we did with the 3's. Examine how we move from one line of this list of calculations down. Well, from negative 8 to 4, you could say we multiplied by 1 less negative 2, which has the same effect as dividing the first result by negative 2. And negative 8 divided by negative 2 is indeed 4. Similarly, 4 divided by negative 2 is negative 2. Let's continue the pattern then. Negative 2 divided by negative 2 is 1. That's somewhat comfortable now because we've already seen that once over here. Negative 2 to the negative 1 power implies that we should be dividing 1 by negative 2. 1 divided by negative 2 is negative 1/2. And then negative 1/2 divided by negative 2. Let's see, first of all, we're taking a negative and dividing by a negative. That will have a positive quotient. And then 1/2 divided by 2 is the same thing as 1/2 times 1/2, which is positive 1/4. Again, we see the similar results that we saw with the 3. We also see, however, something we should be fairly familiar with by now, and that is that when we multiply by negatives, things bounce around the 0. They go above the 0, they go below, and that's what's happening with these integer powers of -2. If it's an odd integer power of a negative number, it appears that the result will be negative. But if it's an even integer power of a negative number, it appears that the result will be positive. And in fact, this will always be the case. Note that just like with the 3's, when our exponents went negative, our powers began moving to the denominator. The negative sign should not be assigned to the denominator, it should be assigned to the entire fraction. Do be careful about this. I know there are some teachers out there, and I'm sometimes one of them, who get a little annoyed and maybe take off a point or two when they see a negative sign placed with the denominator. That really doesn't look appropriate. It's better to have the negative sign associated either with the numerator or even better with the entire fraction. Now that we've seen that pattern development, I think there are 3 rules I want to introduce to you before we start doing a whole lot of examples. The first rule comes directly from that pattern development, and that is that if we have a number raised to the 0 power, the result is going to be 1. The one exception to that is that a cannot be 0. And if you're not sure why that works, let's think about it this way. If you have 0 squared, 0 to the first, and then 0 to the 0. Well, based on the development we just used, 0 squared is 0, 0 to the first is 0, and to get 0 to the 0 power, if we were to do it the way we just did it, we would divide the result for 0 to the first by 0. We can't divide anything by 0. This result is going to be undefined. We're not going to be able to get an answer for that. In the same way, you know that our powers move to the denominator. When we have negative powers, well, a negative power of 0 is also going to be undefined, because to calculate it would put a 0 on the bottom of a fraction. And we know that that has an undefined result every time. So, our rule for any 0 power is that as long as the number involved as the base is not 0, the result of that power is going to be 1. The second rule also comes from the development that we did at the beginning of the ShowMe, and that is that if we have a power that involves a negative exponent, that power will be placed in the denominator of a fraction. Again, a can't be 0, because if it were, we would have 0 on the bottom of a fraction. So if we have a situation like 2 to the negative 4 power, then we'll have 1 over 2 to the 4th. And this will be the step that we use every time we begin calculating involving negative exponents. Finally, a rule that I hope will help eliminate some confusion. If we have an expression that looks like this, we need to rewrite that as a product. In front of the a, we have a negative sign. That negative sign actually is only there by itself because we have a convention about the number 1. When 1 is involved in a product, we know the result is going to be whatever the other number is. And so we don't always write the 1. In fact, in this case, we are not writing a 1, but it would be very, very helpful if we did. So I want you to think of any negative power as negative 1 times that power. This clarifies a very important trick that textbook authors like to play, and of course, if they're textbook authors, they are also ACT and SAT authors, and standardized test authors in general. They love to give you a problem like this. All these negatives drive beginning students crazy. But I think if you use my rule, you'll be able to keep things straight. You see, you should rewrite this as negative 1 times negative 3 squared. Now it's very clear what's going to happen with all your negative signs. You see, we have a multiplication and we have an exponent. In the order of operations, the exponential operation has to be done first. So the multiplication just sits and waits. It does not get involved. This should help eliminate some confusion for beginning students. The first thing you should do is take -3 and square it. Well, that's going to be -3 times -3, which is positive 9. Of course, the -1 multiplication is still there, waiting to be done. And it had to wait because we know in the order of operations we do exponents first. Then to complete the calculation, we do the multiplication that remains. -1 times 9 is -9. A lot of times students get caught up in the fact that if it's an even exponent and a negative number, the result has to be positive. Well, that's true for -3 squared. The problem is that after that's done, there's still a negative sign sitting out there in front. How do you deal with that? Remember what it represents. It represents multiplying the original power by -1. So do that. And I think that'll help you avoid some problems with calculations involving negative numbers and exponents. Okay, the rest of this ShowMe is just a slew of exponential examples. I'm really hoping you can use these to help guide you on homework. These were not taken from any book, although they're based on the book that my students have to use. I'm hoping they will be helpful to students in any textbook or course. For your first example, consider this. We have the opposite of 8 to the 0 power. Remember what I just told you about negative signs. They represent multiplying by -1. 8 to the 0 is still here, of course, but remember our rules now for order of operations. We have to do exponents first. 8 to the 0 power is 1. Then we multiply that by -1. -1 times 1 is -1. So the result of this calculation is -1. Let's take a look at this one. 6 to the -3 power. We know that negative signs mean that our power is going to move to the denominator. They do not mean that the result is going to be negative. In fact, they have no effect whatsoever on the positivity or negativity of our result. That depends on the negativity of the base in the first place and whether or not the power happens to be odd or even. So we have 1 over 6 cubed. Well, we have a division and we have an exponent. Do the exponent first. 6 to the 3rd power. 6 times 6 is 36. 36 times 6 is 216. There's your answer. Note again, 6 to the 3rd power is on the screen in front of you, but it's in the denominator because the exponent was negative. Now consider this one. We have -3 being raised to the -4 power. Note that the parentheses here have an important effect. The negative sign is part of the base. So this means, once again, we have a negative exponent. So this means that our power is going to move to the bottom of a fraction, because that's what the negative sign does. Then we need to consider what the 4th power of -3 is. Well, -3 times -3 is positive 9. Positive 9 times -3 is -27. So -3 to the 3rd power is -27. To get the 4th power, we have to multiply by -3 again. -27 times -3 is positive 81. This is the result of our calculation. Notice, there was a negative in the base, there was a negative in the exponent, but our result is positive. The reason that happens is the negative sign is included as part of the base, and the exponent itself is even. And whenever we have an even exponent and a negative base, we're going to get a positive power. Let's look at that same calculation without the parentheses. Now we have a different problem altogether. The negative sign here represents multiplying by -1. Only the 3 is being raised to the -4 power. Well, proceeding as before, 3 to the -4 power puts 3 to the 4th in the denominator. 3 to the 4th power is 3 times 3 times 3 times 3, which is 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. So now I've got -1 times 1 over 81, and the result of that is -1 over 81. In this case, our base looks like it's negative, but it's not. Our base is positive. The negative sign represents a factor of -1, and since it's a multiplication, it must wait until the power is done first. Then we can multiply by -1. That has the effect of taking a positive number and turning it negative right at the end of the problem. This is the confusion I'm trying to help you avoid with my little rule about negative signs in front of powers. For the last example I'll show you in this ShowMe, let's do a problem where we have to combine some integer powers and some variable powers. In an expression like this, the result is going to still have variables in it, but they're going to be placed differently depending on the powers. For 3 to the -3 power, we'll rewrite that as 1 over 3 to the 3rd power. For r squared, that's a positive power. It belongs in the numerator of its own fraction. Finally, s to the -3 puts s cubed in the denominator of a fraction. Now multiply straight across. 1 times r squared is r squared, times 1 is r squared. On the bottom, 3 cubed is 27. 27 times 1 is 27, times s cubed is 27 s cubed. This is the resulting expression when you simplify something like this. Often, the instruction simplify in a section about this topic refers to rewriting the expression without negative exponents. That's certainly what it means in the textbook that I teach out of. Make sure that you look at the examples and determine what the words simplify and evaluate mean to the authors of your textbook. It is not always the same. Personally, this expression doesn't bother me. I could consider that simplified. But in a section where you're trying to learn about the meanings and implications of negative exponents, the authors are hoping that you'll demonstrate your knowledge by converting it into an expression like this one. Again, make sure you know what the authors and your teacher expect of you when you do work with these things, so that you know how to show them that you understand. That's what they're really looking for. This sort of section appears early in the chapter about exponents in my textbook. I suspect that it shows up fairly early in most textbooks. The first 3 to 5 sections of any chapter in a textbook usually address low-level skills, things that you have to memorize, understand, and practice so that you can apply them. I hope that you found this useful. There are a lot of important places where we have to understand what negative exponents mean. One of the most important places we have to understand it is scientific notation. Scientific notation is something that you will use a lot in chemistry and physics. And the negative exponent issue comes up particularly when numbers are very, very small. Numbers like this number, which can also be written as 10 to the -5th power. You see how much less space this takes up? Now consider the fact that there are some numbers and important constants that have powers of -26. You can literally cut pages out of a printed book or a journal article by using scientific notation. That's just one example of many where this is going to be an important aspect of your work. Again, I didn't know if I mentioned earlier or not, now that I think about it, but if I didn't mention it, you need to understand this also for a very important application called logarithms. Probably someday I'll create a ShowMe for logarithms, but it really isn't a big part of what I teach during the school year, since I teach pre-algebra and Algebra 1 primarily. But if you don't understand negative exponents, you're not going to be able to do the work you'll need to do someday with logarithms. Hope this ShowMe was informative and helpful. Especially remember the rule about negative signs in front of powers. That one could save you a few points on a test.